Okay, so we are going to continue on with chapter 3. Today we're going to do section 3.5 at least in part. It's again a long section. Thankfully there's not much new material in it, but it is a longer section, so it'll probably take 2, possibly 3 days to do it. Section 3.5 is on using the information that we have discussed in the rest of the chapter, as well as algebra, to graph. So we're going to first of all go over some suggested guidelines for graphing. This is essentially a checklist of items that you can find out about a function using calculus and using your knowledge of algebra. It's intended as a guide. It is not necessarily a list of rules. You won't use every item in the guide every time you graph, and you can switch up the order if you like. But if you do complete the checklist, you should have all of the information that you need to make a simpler sketch with all of the important aspects of the function. So some of these items in the checklist require calculus, some of them do not. I will try to remind you of which ones do and do not require calculus. So let's go through them. First of all, if I'm given some function f or y, if you prefer, then from algebra, I know how to find the domain of that function. The domain is all possible values for x. All possible values for x, the independent variable. And there's 2 primary, well, 3 really, because we could possibly include logarithmic functions. You want to look for what values for x make the function undefined. What x values or input variable values make the function f undefined. That's primarily what we're looking at. So I want to think about, is there anything that would cause me to, for example, divide by 0? Division by 0. Is there anything that would cause me to take the square root or an even root of a negative number? Is there anything that would cause me to input negative numbers or 0 into a logarithm? Those are the 3 primary things I'm looking for. Okay, x and y intercepts, those are helpful points. X-intercepts occur where y is equal to 0. Y-intercepts occur where x is equal to 0. I don't need calculus to find those. If I want to use symmetry to kind of make my graphing a little easier or get a better idea of what the graph of a function looks like, there are 2 main types I'm looking for. I am seeing whether the function is symmetric about the y-axis. We would call this an even function. And that occurs when f of negative x is equal to f of x. Okay? So if I input a negative x into the function, does that change the function? If it does, this function is not even, but if it does not change the function any, then the function is symmetric about the y-axis. Other type of symmetry we might look for is symmetry about the origin. We would call this an odd function. And to test this, we want to, again, evaluate f at negative x, and if it happens to be equal to the opposite of the function itself, negative f of x, then this is an odd function. All right, next, we're moving a bit into calculus land here. I want to find horizontal and vertical asymptotes. Now, we found horizontal and vertical asymptotes when we were in, when you took college algebra or pre-calc or something similar. But we're going to specifically use the limit definitions here, at least for the horizontal asymptotes. Horizontal asymptotes occur when the limit as x approaches either positive or negative infinity of the function f of x is equal to some constant. That will tell me the location of a horizontal asymptote. Vertical asymptotes, well, if I want to use calculus, then calculus tells me that if the limit as x approaches some value a, either from the left or from the right, of the function f happens to be equal to infinity or negative infinity, then a, x equals a is a horizontal, or vertical, excuse me, is a vertical asymptote. That is the calculus definition. Sometimes we can figure out, well, what values for x would cause division by 0. That's where I'm going to look for these. I'm going to test this where the denominator, or I should say for x values for which the denominator is 0. Test at x values where the denominator of the function is 0 if I'm given an algebraic function. I'll talk when we get to it about how to discover it using calculus for logarithmic functions. Okay, so there are all of the these are non-calculus features of the derivative. This is a calculus feature, but it does not require a derivative. Everything else on this checklist requires that we find the derivative. So these are items that require that we find the derivative, which means before I find any of these items, then it probably would be a good idea to go ahead and calculate what's the first derivative and what's the second derivative. First derivative tells me about the increasing, decreasing nature of a graph. Second derivative tells me about the curvature of the graph, or whether it is concave up or concave down. Okay, so if I want to find intervals for which the function is increasing, decreasing, or constant, remember we had a process for that. We want to find critical points, critical numbers, I should say, critical numbers where the derivative is equal to 0 or the derivative does not exist. F prime of x does not exist. And then I'm going to use those critical numbers to split the x-axis up into intervals. So I'm going to create what I'm going to call a number line graph. Number line graph here. And I'm going to test values in each interval. And I'm going to remember that if the first derivative is negative, then the graph is decreasing. And if the first derivative is positive, then the graph is increasing. So our two possibilities. If the first derivative happens to be 0 on an interval, f prime of x is equal to 0 on an interval, then we have the case where the graph is constant, we won't run into that case very often. These are primarily what we're going to deal with. Okay, local maxima and minima. I can use either the first derivative test or the second derivative test. Sometimes on your homework, you will be required to use one test or the other. Sometimes on exams, I'll require to use one specific test. But if I don't tell you which test to use, you can choose. Let's see. Maybe I will color code this. Let's make this second derivative test. First derivative test tells me, let's see, if this is my critical point here, if the first derivative is positive to the left of that critical point and negative to the right of that critical point, then this is the location of a maximum. If I have a critical point here, and it just so happens that the first derivative is negative to the left of it and positive to the right of it, then this critical point is a minimum. Second derivative test, I'm using second derivative, of course. And if I test the critical point in the second derivative and I happen to get a negative value, the graph is concave up there, and this critical point happens to be the location of a relative maximum. Oops, concave down, I'm sorry. There we go. Wrote the negative, but said the wrong concavity. And then similarly, if the second derivative happens to be positive at the critical point, then the graph is concave up. So that point will be a relative minimum. You can only use this if you happen to get a critical point where the derivative at that critical point is equal to 0. You cannot use this second derivative test if the derivative at the critical point does not exist. Okay, finally, if I want to know something about the shape of a graph, then I'm going to figure out, well, is the graph concave up or concave down in certain intervals, and where are points of inflection? So points of inflection can only occur, these can only occur where the second derivative is equal to 0 or that second derivative does not exist. Those are the locations where the inflection, or excuse me, the concavity can change. So I first of all start by finding those locations where that second derivative is equal to 0 or the second derivative does not exist. And then I can do something similar to what I did for finding intervals where the function is increasing, decreasing, or constant. I can use a number line graph, except I'm using it for the first derivative. So I can say that if the second derivative is negative on a certain interval, then the graph is concave down like this. All right, if the second derivative happens to be positive on some interval, then the graph is concave up on that interval. All right. After we have gathered all these features, only thing left to do is make a sketch. I can at this point sketch the graph using all of the above features. So let's maybe do an example in another video.